Hello and welcome to the second video on the data mining module, data warehousing and OLAP technology for data mining. In this presentation, we'll cover OLTP, OLAP or OLAP, and data warehousing and data cubes. So let's start with what is OLTP. OLTP is not to be confused with OLAP or OLAP. OLTP stands for Online Transaction Processing. OLTP is what makes so many systems around you work today. All those systems that are from the backends to e-stores, social media, and anything that has a database uses OLTP to capture daily transactions. This, for instance, is when you purchase a product or when you request your social media posts. Small transactions happen against the database. There's typically in SQL. So in SQL, these would be select and insert statements. So we insert in a single row or selecting the top 30 posts. OLTP systems, as I said, are operational systems. So they're designed to be fast at doing this and also as small as possible so that they can remain fast. So they tend to use third normal form relational databases, although document databases are now gaining some popularity using things like JSON. OLTP databases are typically archived off, so they don't give the full picture of all of the data. So once a year's worth of data is saved on the server and it's approaching several gigabytes, a backup might be taken and a lot of that older data removed from the database. It's optimized for access by small queries that are using indexes and typically only returning a small subset of the data. And OLTP systems are typically business critical, so they're essential to the operation of the business, and those small little transactions that they do are what keeps big businesses or small businesses running. So what is OLAP or OLAP and data warehouses and data cubes? A data warehouse is a large store of data accumulated from a variety of sources to support business decisions. And OLAP, which stands for Online Analytical Processing, is how we analyze data in a data warehouse. So unlike OLTP, these aren't small queries, small transactions. These are big queries that are pulling down a large amount of information and analyzing that information. Data warehouses aggregate data from many sources, and those many sources could be other data, could be databases or unstructured data, and those databases may not all be in a consistent format. So when we aggregate this data, then it may need to be normalized and cleaned. So the first stage of creating a data warehouse is aggregating all that data together. The next stage is normalizing that data. And what do I mean by normalizing? I mean minimizing missing values, removing outliers, getting the data into a consistent format. So for instance, a data set on one database may have a measurement in one particular unit, and in another database, it may break that down into either different columns or be in a different measurement. So we can make these columns consistent and put them into one data store, this data warehouse. Data scientists can then use this data warehouse to answer questions. Instead of using the data warehouse directly to answer questions, data marts can also be used. These break down the data warehouse into smaller pieces. These are subsets of the data warehouse which can be used to answer questions. These are obviously, of course, smaller and are simpler to use and can be given to end users or business analysts to extract knowledge from. Unlike a conventional operational system, data warehouses are typically not third normal form. So if you don't know what third normal form is, third normal form is where you have a primary and foreign key, and you remove all duplication from the database by linking data. So if you had an order, you'd have an order record, and then several order records may use the same address, and you can link one address record to several order records to save duplicating that address record. However, data warehouses aren't always third normal form. They can be third normal form, but sometimes they'll be second normal form, and this means that you can have duplicated address records, for instance. So if the fact table was your order table, you could end up having multiple address records that are duplicated. So why would you do this? Because of course this increases the size of the underlying database. This optimizes speed. This makes the data warehouse able to return data faster, summarize that data much quicker. And that really sums up what data warehouses are. They're large, they're massive stores of data, and they're designed to be as quick as possible for OLAP, for analytical processing. So on the left here, we have some data sources. The most typical data source is, of course, going to be a relational database from an operational system. But there might also be other unstructured sources, for instance, documents, other files like audio files, and maybe information that you're pulling from web APIs. So the job of the data warehouser, the person doing the data warehousing, is to extract, transform, and load this information into a data warehouse. So the first stage is extracting the information from those sources. That is then extracted into what is sometimes referred to as a staging area. In the staging area, the data is then transformed. So this is making it useful, which is those steps I mentioned in a previous slide, where you'd change the format of the data, address missing values, address outlying values. Once you've addressed all of those issues with the data and cleaned that data, you can then load that data into a data warehouse. Now, you may load that data into a second normal form star schema. A second normal form star schema is based around a fact table. So you've got a fact table in the middle, and then all the dimensions of the data around the edges. These can all form constellations, so you can have several fact tables, and they may share some dimensions. So there might be a dimension that's common to products that's also common to sales, for instance. Depending on the approach you're taking in designing your data warehouse, whether that be a top-down or a bottom-up approach, you may produce data marts. These are subsets of the data warehouse that just focus on one fact individually. When you're producing data marts, you may actually use a third normal form data warehouse and then produce smaller data marts off of that. So that's another optional way of creating a data warehouse. Once you've created your data warehouse, you can use OLAP operations to analyze your data. This will be done by a data scientist connecting to the data warehouse or the data mart and analyzing that data and using OLAP operations such as roll up and roll down. And then this data will then be presented and evaluated and then displayed to decision makers for taking actions in the business or in research. You can think of these stars as cubes. A data cube can have any number of dimensions, although for sake of visualization, this one has 3 and is therefore a cube. Those are month, product, and region are the dimensions, and the fact could be the sales in this particular case. Data cubes make it much faster to analyze data. Compare that against a relational database, which may have to run several joins to aggregate data to calculate a sum or an average. The data cubes don't need to do as many joins, and this makes them much faster at the expense of storage space, of course. OLAP has several benefits. Most notably is the query performance. This is a gain for both the operational business and the analysis. The operational business doesn't have to suffer when analysis is running and slowing down the database, because they're two separate systems. You've got the data warehouse and the operational database. The analysis doesn't have to wait until the operational business is quiet, and so this is a big gain. And the OLAP queries are operations are optimized for analysis rather than making small transactions. Having a data warehouse and using OLAP gives you a central repository of all your data, and this is unlike your operational database, which mainly have the most current data or the last year's data in. This can have all of the data in one big pot for big analysis. The disadvantages of OLAP are that you need more hardware, so you're storing a copy of your data, and you're storing that copy possibly not as efficiently as you could as well, particularly if you're using second normal form. The data warehouse won't be as updated as recently as won't be as up to date as your OLTP operational database. Your OLTP database is receiving updates continuously throughout the day as every purchase or every post is happening. But in your data warehouse, that's maybe only getting updated once every so many weeks or months. So that means that your analysis may be somewhat out of date. Also, there's the complexity and the effort involved in building a data warehouse. Extracting, transforming, and loading all that data into a data warehouse takes time, and then using those OLAP operations effectively takes some skill and a data scientist or a business analyst to make use of the data warehouse or data marts. Here's a very simple example of OLAP. The simplest example of OLAP can be using Excel or Microsoft Power BI directly on a CSV file or directly on a relational database. So here, just behind my head, is a diagram showing how you can load data from a data source in Excel, or using the data item on the ribbon. And then you can use the pivot functionality, the pivot tables, to run OLAP queries and very quickly summarize and graph that data. So this is a very simple example of OLAP. The OLAP queries are hidden behind the scene, and they're hidden behind me as well. And Axel does those in the background using, I believe it's called MDX, I think. A more complex example of OLAP is a more commercially applicable example of OLAP is using something like Apache NiFi and Amazon Redshift. So with this, you may have several company databases from different divisions of the company or different brands, and you'd aggregate. You'd use the ETL tool Apache NiFi to aggregate all that data and transform all that data, and then load that into Amazon Redshift. So that could be supported by S3 storage. And Apache NiFi is a Java application that can run on a Ubuntu server. And then once you've got all of your data in your data warehouse in your Amazon Redshift, you can connect to it using something like Microsoft Power BI and run analysis on it from there. And then display that on the decision makers in your business for them to make decisions. Hopefully you got an idea what a data warehouse is. But this, I'd just like to emphasize that data warehouses are a separate data store, a separate database, and that data warehouses contain all the historical data. So unlike an operational database that might just have the most recent, data warehouse has all of the historical data, but may not have the most up-to-date data. And data warehousing, the process of data warehousing, is essentially the ETL process: extract, transform, and load. Bill Innon gives us the de facto definition of a data warehouse, and that is a data warehouse is a subject-oriented, integrated, time-variant, and non-volatile collection of data in support of management's decision-making process. So the key We'll go through what each of those elements means, but the key part is that data warehouse is a separate thing and it supports the decision-making process. Bill Inman is actually described as the father, or one of the fathers, of the data warehouse. His approach was a top-down approach, so that's where there's a third normal form data warehouse, and then you use data marts that focus on a single topic. Also hailed as a father of the data warehouse is Ralph Kimball. Both of these early pioneers of data warehouses were working in the late 80s and early 90s, where they solidified the idea of a data warehouse. Ralph was the first to commercialize a data warehouse product called Redshift. And thinking about it, that actually may be the name of the Amazon solution I showed you earlier. Redshift is a homage to Ralph Kimball's first commercial data warehouse, Red Brick. And Ralph Kimball was also an advocate of the bottom-up approach of building a data warehouse. So this is having the data warehouse in second normal form and using the star schema, a constellation of star schemas, to capture all those different facts in the data warehouse, all those different subject areas. So now going through the different elements of Bill's definition of a data warehouse. Subject-orientated means that the data warehouse is organized around the major subjects, rather than in an operational database where it will be organized around forms or around the business process. It makes it simpler to work with from an analysis point of view, and only contains just the data that's needed, that's just important for analyzing and making decisions, which is the ultimate purpose of the data warehouse. A data warehouse is integrated. This means that it contains multiple different data sources. So as we discussed, this could be unstructured and structured data, most likely relational databases, and that the data sources are all combined together into a consistent format to avoid things like differences in naming conventions, whether columns are split or in one column. For instance, name sometimes will appear in a database as first name, second name, and other times it may actually be one column. So sometimes columns may be split and merged. There may be differences in encoding, measurements, and once the data is moved, is transformed in a staging area and placed into the data warehouse, the aim is that it's all in a consistent format. A data warehouse is time variant, and this means that it's got all of the, or as much as is possible, as the hardware allows, and is meaningful for decision making, all of the information from the operational systems over all time. So not just a snapshot that is in the operational system at a given time, but all of the data throughout time. All of the backups will be accessed and placed into the data warehouse. This gives some time perspective over the data, so that an analysis can look at changes over time, over a longer period of time, and identify trends. Data warehouses almost always contain a time element. One of the dimensions will almost always be time, off of one of the fact tables. A data warehouse is non-volatile. This is because it's not using OLTP, so there's not those daily transactions going into the data warehouse. So a data warehouse tends to stay the same day to day, only being updated on a given set frequency. There's big advantages to separating the data warehouse. As I mentioned, having the data warehouse separate from the operational system is beneficial for both. And there's different ways of accessing and using the data that lend to different types of optimization. As we've discussed, the data warehouse is designed for an analysis and pulling back large amounts of data and summarizing that, whereas the OLTP, the operational system, is just pulling small amounts of data on an index, or updating just a few records, or inserting just a single record. The operational systems may also benefit from being distributed. Unlike the data warehouse, that wants to be one central repository, that aims to be one central repository of all the data, the operational systems may be best dotted in separate databases supporting different systems. Thanks for your attention, and we hope you have a great day. The reading for associated to this video is chapters 4.1, 4.2, 4.3, and 4.4. If you could pay particular interest to chapter 4.2.5, which covers OLAP operations. So this is roll up, roll down. There's others too. And this will be about 40 pages. So hopefully this will take you less than an hour. This is one of the bigger bits of reading for this module. So we'd really appreciate if you could take a look through those pages. Thank you very much, and hope you have a great day. Thank you.